LZLite aromatization catalysts gate deactivation. Paper will be given by Professor Gary Haller from the University of Yale. Gary received his PhD from Northwestern University in 1966 with Professor Burwell. He then was a NATO postdoctoral scholarship in Oxford, 1966-67. Since 1967, he's been Professor of Chemical Engineering and Chemistry at Yale. Professor Haller.
Thank you, John. I want to talk about the platinum L-zeolite, which is used for aromatization. It's a fairly recent discovery, at least in the last decade. What's unique about it with respect to conventional reforming catalysts is that it's a metal only, as opposed to a conventional platinum on alumina or acidic alumina or platinum rhenium or platinum tin on alumina, which are bifunctional, involving both the acid sites and the metal sites. But today I will only talk about the stabilization, and particularly the stabilization of nickel, of platinum by nickel. Let's see. Before I get to the stabilization question, let me make a couple comments about effective acidity and the comparison of platinum on a L-zeolite to a platinum on, say, another non-acidic support like silica. And up at the top here, I'm comparing catalysts that are prepared by ion exchange. That's indicated by the I here. This is the calcination number. When you prepare them by ion exchange, you inadvertently, or you, by virtue of that preparation, introduce some acidity, and that is always undesirable. That is to say that if we compare these samples which are prepared by ion exchange to samples that have been prepared by impregnation, which is indicated by IM here, we get much better, much higher selectivities, 74, 63% on the impregnation, as opposed to about 30 to 40% when we have the ion exchange. So that unlike the case of a conventional reforming catalyst where usually you're limited by the acidity, and so putting in more acidity improves the selectivity, putting in more acidity in these catalysts actually degrades the selectivity, at least for aromatization reaction. These should be compared at the same conversion, because the reaction is also very dependent on the conversion. I've indicated the conversion in parentheses here. They're not the same, but they're of the same order of magnitude. So one point is that the acidity is undesirable, and we've tried here to back exchange the ion exchange catalyst with more potassium to remove the acidity, and that's not very successful in this case. If you back exchange with some other cations such as barium, in fact, you can remove the acidity and move these selectivities up to about where they are for impregnation. The second point to be made on this slide is that, well, two more, I guess. If we compare these two catalysts, this one and this one, both are prepared by impregnation, but they have a slightly different calcination temperature, and this one, which is calcined at the lower temperature, has a better dispersion. If we look at the dispersion measured by CO chemisorption, it's 0.6 for this one, and it's about 1 here. And in fact, we get about the same selectivity. But if we look at the relative conversion at 15 minutes and 50 minutes, which is some measure of the self-poisoning by coke, the smaller particles appear to be more stable. They retain about 90% of their activity over this period of time, while this retains only about 80%. That's counterintuitive, right? We have small particles. Normally, one might expect those to be more susceptible to poisoning and sintering, but in this case, the smaller particles are in fact the more stable ones. And then the final point is that there is a big support effect. We don't have the same dispersion here, but we have platinum on silica compared to platinum on L-zeolite. These are compared at the same conversion, and you can see that there's a significantly greater selectivity in the L-zeolite than there is the silica. So the point is that there's the fact that you get the mechanism is probably not different on the silica, but it is substantially higher selectivity on the L zeolite. That is the support effect which one is trying to understand. From a commercial point of view, the Achilles heel of these catalysts is their intolerance with respect to platinum. These are results from Exxon, where they're looking at the benzene yield as a function of time. In the catalyst that decays most slowly, it's in a sulfur-free environment, so this presumably is the inherent coking decay. But then if you add 50 weight parts per million, 100 or 200 weight parts per million, the decay rates go up very much more substantially, and those are pretty low levels of sulfur, right? In a conventional reformer, you might have 20 or 30 parts per million by weight. Parts per million, these are parts per billion, right? In other words, these are parts per billion, and in a conventional reformer, you might have parts per million and still not have decays like this. The decay is not just from sulfur poisoning. The main effect of the sulfur is to catalyze the particle growth. And that's indicated here, where the particle sizes are compared. The particles that are less than about 10 angstroms are the ones that are inside the pores of the L zeolite. It's parallel channels that actually have openings about 12.6 if you ignore the cations. If you put the cations in there, it's just about 10 angstroms. So you start out with a fresh catalyst with most everything inside the L zeolite, and in this particular case, it was one of the sulfur poisoning ones. After 65 hours, you get a large fraction of the platinum, which is outside the channels of the L zeolite. So the main effect of these, because the other point I should have made it is that at the end of those poisoning experiments, they had added only about 1/10 sulfur atom per platinum atom, so that there was, if it were just simply blocking of the surface, you would have had very little poisoning. But the small amount of sulfur catalyzes this particle growth and causes the platinum to move outside the L zeolite. Well, the samples that we're going to discuss are platinum, nickel, and L zeolite, and the intent is to try to stabilize the platinum against these two kinds of deactivations by carbon deposition and by sulfur catalyzed sintering. I'm not going to have time to go into it, but in fact, the preparation of these is by co-impregnation. If we do the preparation that was just discussed, ion exchange, either co-exchange or sequential ion exchange with platinum and nickel, in both cases we end up with most of the nickel outside the L zeolite and the platinum inside, so that the two metals are not together. It's only in the case where we do the co-impregnation do we get the two metals, platinum and nickel, interact, forming small clusters inside the L zeolite. I'm going to spend most of my time talking about these four samples where we keep the platinum content, it's high, but it's constant, and we add nickel to it such that we get up to an atomic ratio of 1 up to about 0.44 platinum, 0.6 nickel. The apparent dispersion seems to be going down as we add the second metal. That is probably the result of the high metal loading we've used here. Because of the parallel channels, if you get a platinum particle on each end of the parallel channel, any platinum particle that's in between will be physically blocked. And since we're keeping the platinum loading constant and then adding nickel, the probability is that we're going to get more than 2 particles per channel. The only evidence that we have for that interpretation comes from the looking at the correlation between the coordination number measured by XAFS and the hydrogen to platinum ratio. For samples that have 1 weight % platinum in them, there's a good correlation between the coordination number and the hydrogen to platinum ratio. Those are the blue lines. If we increase the platinum loading up to 3.5%, it still stays on the same same correlation. But by the time we get these 5 weight %, then it falls distinctly off the correlation because all of these here have about the same coordination, but they have a distinctly smaller hydrogen chemisorption, and presumably that's because now the loading is so high that the probability of having a platinum particle at both ends of a parallel pore, which partially blocks it, is cutting down on the hydrogen chemisorption. We've used several diagnostic tests, physical and chemical, to characterize the platinum-nickel clusters. One of the diagnostic tests we've used is cyclopropane reaction. Cyclopropane reaction was chosen because it has a very different selectivity when you compare platinum and nickel. On platinum, the main reaction is simple ring opening cyclopropane to propane. In the case of nickel, on a real nickel catalyst, you essentially convert all the cyclopropane to methane. If we look at these four catalysts, the selectivity is essentially 100% for propane on the platinum-only catalyst, but it's about 80% on all of the bimetallic catalysts. So that, and to the extent that we do get some hydrogenolysis, it's not to methane, because the ethane to methane ratios are 80 to 90%. On the other hand, if we look at the overall activity, the activity jumps about an order of magnitude when we add the nickel, and then creeps up as we add more nickel, so that we end up having catalysts that have platinum-like selectivity, essentially very selective for ring opening to propane, but they have nickel-like activity. Nickel is a much more active catalyst for these reactions than is platinum. And the point is that there's no evidence for nickel-only behavior. If you had a separate phase of nickel, one might expect to see much lower selectivity for the ring opening reaction. So that is some chemical evidence that the two metals are getting together to form a bimetallic particle. I'll give you some physical evidence and X-half results shortly. Here is another, this is the reaction of interest. It's N-hexane to benzene conversion, and I compare them both at low conversion being below 10%, and high conversion being above 40%. This is what we are interested in commercially, because we want these very high selectivities. We did these experiments at the low conversion to try to get some information about the differential conversions, so we can calculate some turnover numbers. From these low conversions, when we add the nickel, we see that the estimated turnover frequencies drop from about 0.14, not much change at all when we add some nickel, and then down to 0.11 to 0.06 as we move down from a mole fraction of 1 to 0.44 platinum. In other words, for this reaction, we're losing at most a factor of 2 as we add the nickel to platinum, and at low additions of nickel, the turnover frequencies are not changing hardly at all. On the other hand, if we look down here at high conversions, the selectivity is not being much affected by adding the nickel. It drops from 90% down to about from 88 to 82%. But what is changing is the stability against this self-poisoning by carbon. It starts out at 36% for the pure platinum, and as we add the nickel, that is to say, retains 36% of the activity between 15 minutes on stream and 135 minutes on stream. And in fact, the decrease is much less when we add the nickel. So that this is some evidence that the nickel is stabilizing it against deactivation. That only occurs when we look at high conversion. Actually, if we look at low conversions, it's the inverse. Pure platinum has better stability than the platinum and nickel. Why should they be different? Well, that's probably the result of the intermediate that is formed. That is, at the low conversions, you get a fairly large amount of just simple dehydrogenation to C6 olefins. And when you have a lot of the olefin intermediate, then you get a lot of self-coking. On the other hand, at these high conversions, there's almost no olefins, and then the nickel has a positive effect. So this indicates that the nickel can give us catalysts that have activities that are not much different from platinum, selectivities that are comparable, but are much more stable towards, are somewhat more stable towards deactivation by coking. But the real big effect is when we add sulfur, and I'll come to that shortly. The physical evidence that the two metals get together comes from X-ass, coordination numbers. the coordination number, well, of course, in bulk metal, coordination number for both of these is 12. The internuclear distance is 2.77 for platinum and 2.49 for nickel. If we look at one of these bimetallics, coordination numbers now are actually, if anything, slightly smaller than they are pure for the pure platinum, or about the same. That is to say, on pure platinum it's 7, and it looks like it has the internuclear distance of bulk platinum. When we start to add nickel, you have to add these two together, but by the time you get up to, say, 50-50 mixture, the sum of the coordination numbers, platinum, and platinum-nickel, here is about 5.2, which is distinctly less than the 7.1. So there's no evidence that the nickel is increasing the particle size. That in fact apparently seems to be increasing the dispersion. On the other hand, another bit of evidence that you really are looking at an intermetallic compound is that while the platinum internuclear distance stays essentially that of the bulk, the nickel-nickel interaction is much longer than the nickel-nickel interaction in a pure nickel phase, and in fact it's about the length that one would have in the platinum-nickel intermetallic compound. Now, having said that, I must confess that these results are not entirely internally consistent with respect to the coordination numbers. If I really had a 50-50 mixture and I was making a true alloy intermetallic compound, then there ought to be a 2-to-1 ratio for the platinum-platinum to platinum-nickel, or for the nickel-nickel to nickel-platinum ratio, and we don't see that. In a 1-to-1 platinum-nickel intermetallic compound, in that phase, one ought to have a platinum-platinum coordination number 4 and a platinum-nickel coordination number of 8, and a nickel-platinum coordination number of 8, and a nickel-nickel coordination number 4. In other words, the cross product, whether it's platinum-nickel or nickel-platinum, that ought to be twice as great as the platinum-platinum one. And that should be true whether it's a bulk compound or a small particle, because it's just a matter of mass balance. And we don't see that. We don't see that for these small clusters in the L zeolite. When we put the platinum nickel on silica, we do see it. So here I'm comparing, the red is a platinum nickel on silica compared to a comparable composition of platinum nickel and L zeolite. Let's look at the 50-50 mixture. At a 50-50 mixture of platinum nickel on silica, you see that ratio. It's about what the bulk compound should be. It's roughly 4-to-8 and 4-to-8 as it should be. And in fact, these are such large particles on the silica, you can actually determine that it is a platinum-nickel alloy by virtue of its X-ray diffraction pattern. But we do not get those ratios when we put it in the L zeolite. The ratio is not at all what it should be, and I don't have an explanation for that. Although I would draw your attention to the fact that if we look at this internuclear nickel-nickel distance, which in a separate nickel phase would be 2.49, it's about 2.6, both for this situation where we know it's an alloy and this situation where we're not sure what it is. Whatever it is, it seems pretty clear that these are true intermetallic particles that are in the L zeolite structure. Can't see the plot right there. All right, I'm going to skip the next part of this, which was to try to convince you that one of the effects of the intermetallic compound is to exchange electrons between platinum and nickel, which we think we can see in the near edge, and go to the last topic, which is the effect of the nickel on the sulfur poisoning. Here I'm comparing two catalysts, the platinum L zeolite to the platinum and L zeolite after it has been exposed to sulfur, and the same situation for one of the platinum nickel catalysts before sulfur poisoning and after sulfur poisoning. We put a lot of sulfur in here, and those experiments that I showed you from Exxon, at the end of those experiments they used equivalent of 1/10 sulfur atom per platinum. Here we put in 10 sulfur atoms for platinum, so we really clobbered the catalyst to see what the effect would be. And both by electron microscopy and from XAFs, you can see what the effect of sulfur is. The average coordination number goes up, though the intermetallic distance doesn't seem to be much affected. But when you have sulfur there, in fact, the intermetallic distance, the coordination number is essentially unaffected by sulfur. So if you look at these catalysts, the average particle size here is about 10 angstroms, and it goes up to 30 angstroms by electron microscopy. The average particle size here is again about 10 angstroms. You have to add these two together, the platinum, and platinum nickel, so that you see that they have about the same initial coordination number, but it doesn't change after you hit it with sulfur. So this is an indication that the platinum is being stabilized against the sulfur catalyzed sintering. And so the question now is, having stabilized it against particle growth, what has happened to the activity? There's a lot of data on this slide. You've actually seen all of the stuff that's in the light, because it's just the results that we looked at low conversion and high conversion for the platinum and the platinum nickel intermetallic compounds for the N-hexane to benzene reaction before it's been treated with sulfur. The ones in bold are now the comparable results after exposure to sulfur. Perhaps we should, in the interest of time, just concentrate on the high conversion data. The last column perhaps is the most relevant one. That's the relative activity of the before sulfur exposure and after sulfur exposure, so that the exposure to sulfur hasn't changed the selectivity much. It's still of order 80%, but we only got about 2% of the activity left after exposing to sulfur in the case of pure platinum. If we come down to this sample, which has a lot of nickel, again, before exposure to sulfur and after, the selectivity is not much affected. But if we look what happens to the activity, in this case, we still have about 20% of the activity after exposure to sulfur, while we only had about 2% after exposure to sulfur for the platinum only. So this is a clear indication that not only does the sulfur stabilize the nickel towards loss of dispersion, but in fact it retains a good bit of the activity and essentially the same selectivity, and so that there's some indication that these would be sulfur-tolerant catalysts. Well, this is my summary. I skipped over one topic, one summary bullet here, but the deactivation of platinum KL results from two kinds of deactivation: the coat deposition in the absence of sulfur, probably resulting from the olefin intermediates, particularly at low conversion, and from platinum particle growth, which is catalyzed by sulfur. So there's two kinds of deactivation. The addition of nickel stabilizes platinum against both of these kinds of deactivation. The nickel does not simply act as a sulfur guard. If that were the case, there's not enough nickel in any of these samples to just soak up the sulfur so it doesn't get to the platinum. The nickel is metallic and it directly interacts with the platinum, but it does not form a platinum-nickel alloy because those coordination numbers just do not add up the way they would if it were a true platinum-nickel metallic compound. And then this last one, there's some evidence that platinum-nickel interacts electronically with electron transfer from nickel to platinum, is the result of our analysis of our near edge, and that was the 2 or 3 slides that I skipped over in the middle in order to try to get done more or less on time. Thank you for your attention.
Questions on this page?
Myself, University. You mentioned that platinum nickel is electronically interactive. If your assumption is true, let me know about the distance between the mutations in nickel and platinum.
The distance between the platinum?
Yeah, I mean, if there are some interactions, we can assume some influential areas to transfer electrons.
Well, the intermetallic clusters are very small. They can't. They may be longer than 10 angstroms if they stretch out in the channel, but their diameters can't be more than about 10 angstroms, right? And the X-AFs indicate that there's a rather intimate mixing of the platinum and nickel, but not actually forming an intermetallic compound like platinum nickel.
Your idea is that they are interfaced.
No, actually, I think it's more than just interfaced. If you only had a nickel particle and a platinum particle with an interface, then those coordination numbers are much too low. All right, the cross coordination numbers. They're not high enough to be a pure intermetallic compound, but they must be one in which there's both. There may be, say, a nickel-rich particle up against a platinum-rich particle, and both of which are only about 10 angstroms in dimension, something like that. But there cannot. The cyclopropane results, I think, clearly show that there's not a separate nickel phase. If there were a separate nickel phase, we would see some contribution to the cyclopropane to methane reaction, which we don't see. Has such a high activity compared to platinum that ought to just stand out. So since we see no separate nickel phase, either chemically or can account for it by X-AFs, I think that this is some cluster which is inside the L-zeolite, but not homogeneous in the way an alloy would be. And in that case, even if you had 2 to 10 angstrom particles, I think electron transfer would not be an unreasonable expectation.
Short question. What was the condition for the sulfide?
Oh, it was 500 degrees, and we used dimethyl sulfide as the sulfide agent. So they were exposed to dimethyl sulfide by just carrying the vapor in a hydrogen stream, and then they were held for 1 hour at 500 degrees to strip off excess sulfur. Actually, when you looked at the sulfur afterwards, not much sulfur came off, which means that a lot of the sulfur must be retained on the zeolite, not on the metal, right? For 2 reasons. One is there's just not enough metal to hold all the sulfur. Right? We put in 10 atoms of sulfur for every metal atom. And secondly, there's no evidence in the X-AFs for any backscatterings from sulfur on either the nickel or the platinum. So the majority of the sulfur must be somewhere on the zeolite.
And on metal, you expect to have the surface sulfur.
Yes, because there's no.
Sulfide.
That's right. If there were any sulfide formed, we would surely see that.
You don't see that.
We don't see any backscattering. So there's very little sulfur on the metal.
Thank you.
Actually, that might be the mechanism by which it catalyzes the sintering, right? It may be that the sulfur actually competes with the metal for sites on the basic zeolite, and that sort of de-anchors the metal and gives rise to the sintering.
Oh, John from postdoc, would you give me a little bit detailed explanation how the sulfur sinkers platinum?
Well,
and why did you choose nickel? Nickel is the best one to prevent sintering. Why not cobalt or iron?
well, I don't know why. We haven't tried cobalt and iron. Let's take the first one. I don't think we have any clear understanding why sulfur catalyzes the sintering process. The one proposal that we and others have made is that there is some interaction with the L-zeolite surface of the platinum, for which the sulfur atoms compete. They sort of they as it were de-anchor the metal and allow it to move around at the reaction temperature, which is quite hot. That's a possibility anyway. And why nickel? Well, there are a variety of reasons that we we chose the first row metal. There was, first of all, there's evidence from Wolfgang Zocker's work that if you take elements like chromium and iron, you can stabilize platinum against a particle growth in Y zeolite. So we thought we might be able to do it in L zeolite. That was one consideration. Another consideration was the fact that we had, for quite different reasons, been studying platinum, nickel, and silica. So we had all this reference work on a relevant catalyst, and so that's the reason we tried nickel. Now, I'm sure that I would not be surprised that iron and cobalt would also work. But in fact, all of those metals are ferocious hydrogenolysis catalysts that you might think you want to go further down in the periodic table. And so the obvious ones there is to go and use tin and rhenium because they are used in conventional reforming catalysts. And tin ought to be the one of choice because it is poor hydrogenolysis catalyst. And if you can then also anchor it, it might have some very desirable properties. And we are now studying platinum tin and platinum rhenium to compare to platinum nickel, but I don't have those results.
You mentioned that there is electron transfer between platinum and nickel due to the formation of bimetal. Was there indication for that by near edge spectrum?
Yeah, that is what, those are some of the results that I didn't show you, which I can quickly do, I guess. Show you one of them anyway. So, if in fact there's electron transfer, what you expect is that you get a higher intensity at the edge when you make a density of empty or vacant states there. So in this case, we're comparing the intensity right at the edge for nickel foil, and as we add nickel to platinum, in fact, that intensity goes up quite dramatically, as it would if there was electron transfer from the nickel to the platinum. Now, I should hasten to add that if you look at the platinum edge, it's not so clear cut. For the L zeolite, we've looked at the whole range of compositions for platinum, nickel, and silica, and then we get the same result. In that case, systematically, you see that the intensity of the nickel goes up, as it should if it were losing electrons, and the intensity of the platinum goes down, as it should if there was, conservation of electrons. That happens for the larger particles on silica. In the L zeolite, we see a similar effect when we look at nickel, but when we look at the platinum, it's not so clear. And that has, again, to do with the small particles and other things that we don't understand.
Jason for High Game Corporation. Have you tried the case of PT nickel alloy case? You already mentioned nickel is not alloyed with the platinum. But how about the result of the case PT nickel alloy?
Well, we haven't tried it because we haven't found a preparation technique that we can make a true alloy. That's the problem. We actually, at the beginning of these experiments, presumed that the correct preparation was to do ion exchange. And so we started out doing ion exchange of platinum, reducing it, and then ion exchanging nickel and reducing it, thinking that the platinum would be the site at which the nickel would be catalytically reduced, and we would get this decoration with the platinum with the nickel. That didn't work. If you put the platinum in first and then ion exchange the nickel and reduce it, all the nickel just moves outside and makes big particles. If you do a co-ion exchange and reduce that, the platinum stays in, the nickel moves out. If you impregnate it, now apparently I would guess this has to do with the acidity, right? Because in the case of the impregnation preparation, then you have a basic zeolite that remains basic. In the case of the ion exchange, you put a little acidity inside, and apparently a little acidity is enough to let the nickel, during the reduction step, all move outside the L zeolite. So the best we've been able to do is to get make the clusters by co-impregnation, but we haven't yet made a platinum nickel alloy, at least not based on what we see from the XF. So I don't know what the result would be if we had a true alloy.
Any more questions? If not, I think we'd like to thank Gary for his interesting presentation.